Hey, I'm CJ, and welcome to my workshop. This is a place where we play around with technology and a bunch of other things. So, today we're talking about power limiting NVIDIA GPUs. And in a nutshell, why you would do this is to save some money or put more compute in the same amount of area. And, I think both of those things are interesting and good. For example, in the US, we often have 15 amp circuits at 120 volts. So this is around a 1.4 kilowatts of power. And if you want to put as much compute as you can in that amount of power, tuning your GPUs for that might make a lot of sense. You could fit more GPUs and more compute in the same area. You may want to do that similarly in a data center where old server racks are about 5 or 6 kilowatts. And if you can optimize your GPUs, all of a sudden you can fit more GPUs in a data center. In older racks that are not as power dense and that maybe you can get for a relatively cheap price compared to the new racks that are more power dense and built for GPU application. It really depends on your specific needs, but at least it's a possibility. So compute density is one reason, and the other is, well, I think just running things efficiently is good on the whole. So finding a workload that you're doing and optimizing that workload to make sure it's really good with the amount of power you're spending, to me that just makes a lot of sense. And this ties into so many other things, whether it be how do Apple devices compare to NVIDIA devices in terms of efficiency, or any device compared to NVIDIA in terms of efficiency. Maybe it's an NPU. And I think this is going to be the direction that we start to go and see as the workloads become a little bit more solid. And I think we're starting to see some of this happen. So this is why I'm super interested in efficiency. And we're going to take a look at it today and try to optimize some workloads, or at least see how workloads respond to different amounts of power being given to them by the GPU. Or rather, how much power you're giving the GPU to do the workload. So there we go. That's what we're going to be taking a look at. Today we have a 3090 on the bench, and we're going to test that between 150 watts and 350 watts. And we're going to do that in 5-watt increments. So we'll have data between all of those points. And we're going to look at 4 different kinds of workloads. One is large language model workload, the vision models, speech to text, as well as diffusion models. And with that, I think let's just dive straight into the numbers. So here we have the results for our 3090 across our entire benchmark suite, and I built this little web page to show the data and be able to play with it and explain the data in real time. And I will put this up on a website so you can play with it yourself as well. And just going through the basics, you can see my test configuration here, and the only thing to note that is not mentioned is for the language and vision models, all of these are run at Q5KM, and for hearing, that is run at Q80. So that is the quantization that we're running at for all of these benchmarks. Here we're looking at Llama 3, 8 billion, and immediately we can see as our power limit increases, we get more tokens per second. And that's what we're looking at here. We're looking at wattage versus tokens per second. But at some point you can also see this levels off quite quickly around, this range here, 230 to 250 watts. And we can see, okay, so at 250 watts, we get 93 tokens a second, and all the way at the maximum, we get 101. So maybe there's a 5 to 10% increase in overall tokens per second, but you're pushing the power up another 100 watts to do that. And just to show a little bit more clearly, we can zoom in a bit and disregard that first, but we can see this very obvious, curve right here. And maybe what's useful is we can take a look at, the generation tokens per second per watt. And we can clearly see in terms of tokens per second per watt, we get this nice peak right at 250 watts. But I would even say, this whole kind of area right here, we're seeing like very solid efficiency generally for the GPU for this workload. And let's take a look at the rate of change. And the rate of change is just how fast tokens per second is growing over time. And we can clearly see also, we stop growing quite as quickly, right? Around 240, 250 watts. And that's exactly the moment where the efficiency is the best as well. And we can also see the growth kind of levels out here, and you're just going to kind of get a different set of growth. But initially, you get really great rate of change, 10%. That's pretty amazing, all the way down till you get 1% gain. So that's a 10x difference between these two, and that's quite significant. So let's go back to our single chart here, and let's look at some other metrics as well. So I think another one that's really interesting is our time to first token. And this is more a metric that I would say you might want to use if you're deploying a system potentially. Is you don't want to keep people waiting, that kind of thing. Tokens per second actually maybe doesn't mean that much to you. But it's also very similar when we take a look at this in terms of the rate of change. Here, instead, we're looking at negative values, how much faster we are getting time to first token. But again, in that same 250 watt regime, it's much better. And I would say that, we're looking at a time to first token here of 100 milliseconds. And at 350 watts is 88 milliseconds. That 10 milliseconds is probably not going to be a super big deal. But you compare that to 150 watts where it's 300 milliseconds versus 100 milliseconds. It's a big change. And finally, let's take a look at elapsed time is how long the benchmark took. We had 12 different prompts. And again, it's showing the same thing right in this regime. Really good. But I also think elapsed time is good because it's kind of showing you a bit more end-to-end throughput. How many responses did you get overall? So now that we've kind of looked at this first piece of language, I want to take a look at Gemma 2 because you'll notice it's actually quite different. And if we look at the generation tokens per second, we'll start there. And immediately we can see that curve completely shift. That curve has shifted way out to 300 watts, basically. You kind of see these two regimes again, this big linear regime, and then there's some inflection point around here where it flattens out. And if we take a look at the rate of change, this will be probably pretty obvious. Again, at that 10% increase, and then right around here, we level to 3%, and then all of a sudden we drop off a cliff to 1% or less. So I think it's interesting is we see that for different sized models, running your GPU at different power limits affects it quite significantly. And we could look at all of the same data as before, but it more or less will line up to around this 300 watts for this particular workload. And again, time to first token, we can see right around 300 watts, 300 milliseconds versus 288 at its best. And then, you could even cut it back a little bit and probably still get something interesting. And let's take a look at the tokens per second per watt as well. And again, it peaks right in this area. But I like this curve a lot because it kind of just shows you maybe a general area that you might want to target in terms of your GPU's efficiency, regardless of all the other metrics. Of course, you want to keep your users happy in whatever way. So you have to hit those first, but then finding what power target is good for that is pretty interesting, I find. And we can do something similar for vision, and we'll again look at generate tokens per second. Moondream is a very small model, and you can see the variation is a bit higher, likely just because the GPU is effectively super overpowered for how small this model is. And we do get like a large increase in tokens per second overall throughout the whole thing. But I would say like you can kind of just see like around this 200 to 230 watt mark. It's pretty efficient, and you're already at nearly 200 tokens per second. Do you really need more than that? And especially when you look at time to first token. It's like in this regime where you get 400 seconds or 400 milliseconds to get it versus 395. So there's effectively no reason you would even want to run Moondream on a 3090 at a power limit as high as 350 watts. It just doesn't make sense. You're consuming way more power than you absolutely need to. And that's to say, like, even at this power limit, we're actually only consuming about 175 watts. And at the max, we're only consuming 200 watts. So the difference in power on these small models is significantly less because you're just not being able to max out what the GPU is capable of, at least for a GPU this big and relative to a model this small. And similarly, like we can take a look at Whisper, and I think generally we'll kind of see the same kind of thing. Whisper is, again, relatively small compared to, like, say, a 27 billion parameter large language model. And, again, we see this same curve, the average speed up right around that 200 watt mark. But again, like each workload has like slightly different limits. And what I would say is, here we're only testing a single batch. So we're only testing like one prompt at a time effectively. Batch size probably impacts these numbers as well, but that's just another thing that can be tested for your workload and optimizing your workload and optimizing power for your workload as well. So, we get really good speed up into 250 watts, and then effectively after that, it doesn't matter anymore. And the elapsed time of this one is super obvious. You have this like really steep curve going down to 220 watts, and then it effectively bottoms out after that. And you can kind of just pick and choose, anything in this area that seems good to you. Let's now take a look at creation, specifically the Stable Diffusion workload. And initially it kind of seems like, oh yeah, 200 watts is so obvious compared to the other curves that we've had so far. But I think it's a little less obvious than you think, especially as we just bring this in a little closer. Yes, the steepness of the curve definitely changes there, but also this part of the curve is still quite steep, and it does just flatten out at the very end. When we look at compute time to image, it becomes a little bit more obvious in some ways. 7 seconds at 225 watts versus 5.7 seconds. This is a pretty big change, a second and a quarter better. So this is a workload where I feel like you have to decide for yourself a little bit more where exactly you want to sit on this curve. Are you trying to serve images fast or slow? And or maybe the speed doesn't matter as much, and maybe more compute density is something that you care about so you can serve more people. That's always a possibility. And of course, with Stable Diffusion, there's also something like Lightning, which you could run in a second and a half, or up to 1.2 seconds, and that could be a good option as well. Thank you for sticking through all of the numbers and discussion. And I think overall, the most interesting thing about all of these numbers is that you can tune your GPU for the workload that you want to run. Maybe you're running a wide variety of workloads, in which case maybe it doesn't matter. But maybe you're running Stable Diffusion most of the time. Or maybe you're running Llama 8 billion most of the time. And if that's the case, yeah, setting the power down a little bit is pretty good. Something useful to do. And overall, I think this project is really interesting. And mainly because efficiency is important. And like workload tuning is the first step in getting hardware that is meant for certain workloads. And the more that we know what those workloads are that are going to serve real people and make an impact and difference in their life on a daily basis, the better, more efficient hardware that we'll get. So we don't need to burn thousands of kilowatts or hundreds of thousands of kilowatts to do so. And to me, that's really important. Of course, we should do better on clean energy generation, but efficiency no matter what matters. So I find this really interesting, and this is going to dovetail into a bunch of other topics as well that I'm going to start going into. And a lot of it is kind of regarding this workload tuning to begin with. So it'll be, well, I want to compare NVIDIA GPUs over generations for different workloads. Because again, you might be able to find a bargain GPU that works for your workload by doing that, or whatever it might be. And also, I want to compare things like Apple Silicon and Macs to GPUs, because it's a very efficient platform, and if it serves people well, that's fantastic, and we should consider that. And maybe that drives some of the industry as well. And in addition, overall, I think competition is great, and I really want to see AMD, Intel, NVIDIA, Apple benchmarks, as well as whatever hardware companies come out with things next. And hopefully we can begin to have a more homogeneous set of software that works across all of the platforms very easily. And then people can compete not on the software that they write and the software stack that they have, but on the hardware that they're providing us. And I think that will be really helpful for the industry as a whole. And with all of this, there's like another fun project coming down the pipeline for me. And that's this little Raspberry Pi plus NVIDIA P102-100, the old crypto mining card that we looked at last time. And this is probably somewhere between $150 to $200 in total. And I'm hoping that it can make a little powerful AI rig for very cheap. And the next step on top of this is going to be exploring solar-powered AI machines. This will be one of them, and of course Mac Minis and MacBook Pros will be others, because I think it's just an interesting topic. So that's what we're going to be exploring in the near future. And I think there's also generally the thing about cost that I want to explore within all of this too, is it has to make financial sense. Whether it be you running in a data center or whether it be you running as an individual. For hobby is fun, but also I think we want to make things that are like valuable on the whole. And I think AI does have a lot of potential to make computers much more valuable and useful and easier for most people. So that's what I'm most excited about. And we're going to explore some of these hardware topics along the way. So I hope that you enjoyed and you learned something today, and I hope you have a wonderful rest of your day. And I'll talk to you soon. Thank you.